Okay, let's take a look at our second type of improper integral. And on this one, we're not dealing with an equation or an integral where one of the limits of integration goes to infinity. We're dealing with an issue somewhere in the middle of the graph, meaning not at the infinities. So the first thing we want to do is graph this function f of x equals 1 over the square root of x minus 2. And it says on the interval from 2 to 5. There might be a typo on your paper where it says 0 to 5, but we meant to write 2 to 5. So this is the graph. I have a vertical asymptote here where x equals 2. And then if I were to graph this entire branch, it would look like this. And I don't know that off the top of my head. I put that in my calculator to see what it looked like. And of course, if I stopped it at 5 right here, I would get just this section of the graph. So I have no problem here at 5. I have a hard endpoint. However, at 2, I have a vertical asymptote, which creates the improper integral. So we have a VA, vertical asymptote, at x equals 2. So if I were to solve the integral from t to 5 of 1 over x minus 2, I end up having to anti-differentiate. And of course, this is x minus 2 to the negative 1/2. So I add a degree to the positive 1/2, and I divide by the new degree to get a 2, and evaluate it from t to 5. I'm going to get 2 times 5 minus 2, which is 3, to the 1/2, which is the square root of 3, minus 2 times, now t minus 2 to the 1/2. So this is our integral, but now what we really need to do is take the limit as t goes to 2 from above. And it is critical that you put in this 2 from above when you do your limit setup on your free response problem on the AP exam, on a test, or on the gateway. You must have this proper limit set up. And you know you're coming from above because your t is your bottom limit of integration, and to go towards t, you're coming from above. So you need a plus symbol here. So now if I take this limit as we go to 2 from above, something slightly higher than 2 minus 2 is effectively 0. So this term is going to zero out, and my limit will be 2 times the square root of 3. Well, we have just found that this improper integral is convergent, and it converges on 2 rad 3. So let's take a look at type 2 improper integrals overall. The first type is that there is a discontinuity at the upper limit of integration, which in this case is b. What you need to do is set up the improper integral with the limit such that t approaches b from below. And you see that negative means from below. The reason why it's from below is the t is your upper limit of integration, and you're coming up from your lower limit of integration. So you're coming from below to get to t. And so provided the limit exists, this limit here that you just set up will equal the improper integral. Second scenario is when your lower limit of integration creates the vertical discontinuity. And in that case, you set up a limit as t approaches a from above. And again, it's from above because you're coming in towards t from the upper to the lower limit of integration. Remember, when you set up these limits, you must have the proper symbology here or you will not get it correct. If f of c has a discontinuity at c, where c lies between your lower and upper limit of integration, then what you need to do is split your integral into 2 parts at c. So you're going to have the integral from a to c plus the integral from c to b, and you'd set up a separate limit notation for each of these, and you'd take the limit for each. And I will tell you this, if either one of these gets you a does not exist or one of the infinities, then your improper integral is divergent. If you get a number for each of these, then your improper integral will converge to the sum of these 2 limits. So let's try this with the natural log of x. And of course, we know how to graph ln of x. Looks like this. And it has a vertical asymptote at 0. So it looks like our lower limit of integration is what makes this an improper integral. So what I'm going to do is I'm going to set up a limit as t approaches 0 from above. And remember, we're coming in from above towards our 0 here. So that's why we have the plus sign, of the integral from t to 1 of the natural log of x dx. And now you have learned how to integrate by parts the ln of x, and you may have that memorized by now, to be x ln of x minus x. And so you want that to go from t to 1. Don't forget your limit notation. That is critical. T approaches 0 from the right or from above. And now let's evaluate. We have the limit as t approaches 0 from the right, 1 times the ln of 1 minus 1, and then let's subtract out our lower limit of integration, t ln of t minus t. So ln of 1 is 0, so this term goes away to 0, so I'm left with negative 1, and then let's distribute negative 1 minus t times the natural log of t plus t, and of course this is the limit as t approaches 0 from the right. If I did direct substitution here, I would get effectively a 0 times a negative infinity plus a 0. So the real question is, what wins out here? Is it the 0 or is it the infinity? And what we can do to determine that is do a L'Hopital's rule on this. So if I went ahead and did a L'Hopital's rule just on this middle portion, I would get out that the limit as t approaches 0 from the right, and I'm going to rewrite this as, I'm not going to worry about the negative sign, I'm just going to look at the expression, but I'll rewrite this as the ln of t divided by 1 over t, because multiplying by t is the same thing as dividing by its reciprocal. So now is actually when I apply L'Hopital's rule. I have the limit as t goes to 0 from above, and the ln of t differentiates to 1 over t. 1 over t differentiates to negative 1 over t squared. And by the way, I didn't even comment, I can apply L'Hopital's rule here because this goes to negative infinity and this goes to positive infinity. And when I have an infinity over an infinity, it is a L'Hopital's rule problem. So now I can simplify this by multiplying by negative t squared over negative t squared. My denominator cancels and my numerator just goes to negative t. And as I approach t from above of negative t, I'm going to get 0, which means that this whole term here zeroes out, and this term of course zeroes out when I plug in 0. So my limit is going to be negative 1, and I have a convergent improper integral, and it converges on negative 1. Okay, for this next example, I have to determine where I have an improper integral. So let's go ahead and graph 1 over x minus 1. And I have a vertical asymptote at 1, and then it's a basic hyperbola here that looks like this. So I'm integrating from 0 to 3, so my issue is that I have a vertical asymptote at 1. So what I'm forced to do is to write this in two separate integrals. I'll have the integral from 0 to 1 of 1 over x minus 1 dx, plus the integral from 1 to 3 of 1 over x minus 1 dx. And now I'm going to set up my limits. My first expression requires me to take the limit as t approaches 1 from below. And remember, I'm going up towards 1, which is why my limit is from below. And of course, I have the integral from 0 to t now of 1 over x minus 1 dx, plus on the right side, I need, actually, let me erase this integral sign because I wanted to write my limit first. So I need to write in my limit here as t approaches 1 from above, and in this case I'm coming from the upper limit of integration down to 1, so I'm coming from above towards 1, and my integral symbol is integrated from from t to 3, and of course I have 1 over x minus 1 dx. That is an x minus 1 there. So then when I integrate each of these, I'm going to have the limit as t approaches 1 from below. This goes to the natural log of the absolute value of x minus 1 from 0 to t, plus the limit as t approaches 1 from above of the ln of x minus 1 from t to 3. And now I can start doing my substitutions, or my evaluations. So I have the limit as t approaches 1 from below of the natural log of t minus 1 minus the natural log of 0 minus 1. These are in absolute values, of course, plus the limit as t approaches 1 from above of the natural log of 3 minus 1, which of course is 2, minus the natural log of t minus 1. Now I start evaluating. So when I approach 1 from below, and I plug in 1 from below in here, so a number just below 1 is maybe 0.99999, minus 1 is effectively 0. And the ln of effectively 0 goes down to negative infinity. I can stop right here because as soon as I have one component not converging, my entire improper integral must be divergent.